In this video, we're going to be talking about the post-lab analysis for our specific heat capacity. The first question asks, using the chart with the known heat capacities and your calculated values, identify your two metal samples. Explain how you came up with that final decision. We spoke about this at the end of our previous video, where you have now calculated the specific heat capacity in joules per gram degree Celsius, and you've gotten a number. Now, technically, you've gotten two numbers because you've done two trials. So you could calculate the average of those two to be able to find the value that comes up closest to a specific metal. Now, let's say you came up with a value of 0.95. Well, 0.95 is close to air. Please don't tell me your metal sample is made out of air, because air is a gas and your metal sample is not made out of air. But 0.95 is very close to 0.895, and so you could make an estimate that it's aluminum. So you're going to use those values to find out what the substance is that we're dealing with. It's very important. Place the number, so you got two answers. Place the number of your cube plus your answer. And you're going to have that two places. Because I don't want you to tell me, oh, I think my cube is gold, but then I don't know what the number is, because every one of those numbers is a different substance. So make sure you give me the number of your cube and your answer. Now, if you come up with, let's say, 0.35, well, 0.35 value is close to 0.38. It's close to 0.38. It's also close to 0.38. Lots of these are very similar. But brass, you can use color as your secondary property to determine what the substance is made out of. Brass is more of a gold color, copper is more of a brownish color, and then zinc is more of a silver color. So you can use color as your secondary property in choosing your substance. This here is very, very important to the lab, because I'm going to be specifically looking at that, making sure that you came up with the right substance for your in your calculations. Use your calculated value and the known value to calculate the percent error. Find the difference in the calculated known values and then divide by the known value. So let's say that my answer was, as I mentioned, 0.350 joules per gram degree Celsius. This is what I got. Let's say this is what I got from my experiment. Now, this is not, you can put your number here, so the number of your sample plus your number, but then give me your answer too. So your answer is going to be what you think the substance is. So there'll be three things here: the number of your cube, what you think the substance is, brass, copper, gold, plus the value that you got from your experiment. Now, let's say that I got 0.350. So I'm going to find the difference in my calculated value. That's what I calculated. And I'm going to have 4 experimental errors. Unless if you want to use an average value, then you can just do 2. And that would be perfectly fine. So 0.350 joules per gram degree Celsius. And then it says find the difference. So subtract. Let's say that I thought it was brass, so I'll put 0.380 joules per gram degree Celsius. I subtract those first, then I divide by 0.380 joules per gram degree Celsius, and then I multiply by 100. We do the subtraction first, then divide, and that will give me my percent error. You're going to do that at least twice, or if you're using your average value from your experiment, average just means that you're taking your two values that you got from your calculations, adding them up and dividing by 2. That's perfectly fine. What did the percent error tell you? So if we're less than 10%, then that is very, very good data. That means we took very, very good data. Higher than 10% means that we probably could have done a much better job in our measurements, or lab technique was poor. And we'll talk a little bit about that. List 3 potential sources of error. So there are some sources of error that are going to be related to assumptions that we made during the lab, and we're going to discuss those. So one of the things that we did during the lab is, before putting our cubes into the calorimeter, they were sitting in boiling water. Because they were sitting in boiling water, we said the temperature of the metal cube was about 100 degrees Celsius. Now, we measured this to the nearest tenth, but we had to reach in and pull these metal cubes out before putting them into the water. As we reach in and pull these metal cubes out, as soon as they get into the surrounding air, the temperature begins to drop. So we made an assumption that whatever the metal cube temperatures were inside this boiling water was the same temperature right before we put it into the calorimeter. That's probably not true, because as soon as we pull it out of the boiling water, the temperature of the metal cubes begin to drop. Now, what do we know about metal? Metal has a very low CP value, so it will change temperature quickly. Because it will change temperature quickly, most likely that temperature is dropping before we get into that water. Remember, we use the change in temperature of the metal, assuming that that temperature was the same as the boiling water. By the time we get it into the calorimeter, that could be a source of error. Another source of error is we carefully measured how much water was in the calorimeter. And now all of a sudden we reach in, we pull the metals out that are surrounded by water, and now we've added water to our calorimeter by, that is the water that's surrounded by the metal. So when we grab the metal cubes with those tongs, those metal cubes are surrounded by water, and we put the metal cubes into the water, so we've probably added a little bit of water to that calorimeter. The next big source of error, which is also connected to the assumptions that we made, is we said all the energy that's leaving the metal, all of it went into the water. Now, let's look at this process. I grabbed those metal cubes with my tongs and I pulled them out of the boiling water. Well, those metal cubes are now giving the tongs energy because they're touching each other. And then those metal cubes in the air are heating up the little air molecules that are surrounding the metal. And then when we put the metal cubes into the calorimeter, the metal cubes are actually sitting on the calorimeter, so are giving energy to the bottom cup of the calorimeter. So we said all the energy went into this water that's in the calorimeter. Well, that's not true, because some of the energy went to the tongs. Some of the energy went to the surrounding air as we made the transfer. Probably a lot of energy went to the bottom cup of calorimeter. So not all the energy went into the water. That energy went other places. It's impossible to find out or calculate the amount of energy that went into these other places. So we make an assumption. We assume that all the energy from the metal went into the water in order that allows us to do these calculations. And what we're going to find is it's pretty close to all the energy going in from the metal into the water because of our low percent error. But it's not perfect. It's a source of error based off an assumption that we made. The other sources of error was maybe if I wasn't careful putting this water in, maybe some of the water could have splashed out. Maybe we weren't reading our thermometer that's got markings, and let's say that it went up to this spot right here. Maybe we just used the whole number instead of the nearest tenth, and we weren't real precise in our thermometer readings. Another source of error that we could have made by assuming is about the temperature of the boiling water. Maybe some of us assumed that the temperature of the boiling water was 100 degrees Celsius instead of measuring it. We needed to make sure that we measured that. That could be another assumption that we made, is that the temperature of the water was at 100 degrees Celsius. Well, if it's pure water and the atmospheric pressure is 1 atmosphere, yes, it will be at 100 degrees Celsius. But we didn't use pure water, and the atmospheric pressure may have not been 1 atmosphere, so it may not have been 100 degrees Celsius. But you might have measured the temperature of the boiling water, so that would not have been an error. A recycling company, question number 6, decides to use specific heat as a way to separate metals from each other. Do you think that this is a reasonable plan? This took a lot of time and energy to be able to find out what the type of metal is using specific heat capacity. They probably would not go through all this just to separate out. What would they use? Well, something that's easy to use is color. Something that's easy to use is whether it's magnetic or not. So there are some other easier things to use to separate metals. And those two you could talk about here. Up here you could talk about that it's probably not an efficient way to separate out for a recycling company. And then if you have a minute or two at the end, check with your classmates. Look at their data, their calculations in terms of, did they come up, anybody use the same sample? Did they come up with the same type of metal that you came up with? This question asks for about the styrofoam versus the metal calorimeter. We did not use the styrofoam. I wanted you to do 2 trials with the metal calorimeter because it's more precise rather than using the styrofoam. If we use just a styrofoam cup, what happens, and this is what this is talking about here, is energy will be able to flow out of or into the styrofoam cup because it's not isolated. That's why we've used the calorimeters, because now we've got 2 cups, and then that's also isolated by styrofoam so that no energy can get out and no energy can get in, to give us better data for our lab. I hope this helps in understanding the post-lab analysis for the specific heat capacity.